Hello students. So in previous section on open sets, we defined concept of open set. We have proved that in any metric space X, empty set and whole set X are open. Arbitrary union of open sets is open and finite intersection of open sets is open. So due to this result, every metric space is a topological space. Today we are going to study some more results about open sets. So our first theorem about the open set is now today's first result. Every open sphere is open set. Every open sphere is open set. So every open sphere in a metric space XD is open set in X. Okay. So we'll prove this. So for X belongs to X and R greater than 0, SRX is equal to Y belongs to X such that D of Yx less than R, the open set, open sphere in X. What is our claim? SRX is open set. That is to show for any Y belongs to, okay, that is to show for any Y belongs to SRX, there exists some R1 greater than 0 such that SR1Y is contained in SRX. So if I take Y equal to 1, S1, if Y equal to X, then SRX is contained in SRX. Case 2, if Y is not equal to X, Y is not equal to X, then D of Yx is less than R. D of Yx is less than R. Take D of Yx, and in fact 0 is less than D of Yx less than R. D of Yx is not equal to 0 also. So take 0 is less than R1 is less than R minus D of Yx. Okay. Then to show SR1 Y is contained in SRX. So we have open sphere say SRX. This is my SRX interior points. If I take Y to be some point here, what I am doing, I am taking R1 is to be this one, and this is my D of Yx distance. R1 is less than R minus D of this. I am choosing that R1. Okay. So take now Z from this to be arbitrary point. So then I have to show that D of Zy is less than R. D of Zy is less than R. So let Z belongs to SR1 Y. This implies d of zy is less than r1 and r1 is less than r minus d of yx, which implies, if I compare this, d of zy plus d of yx is less than r, right? Now by triangle inequality, d of zx is less equal to d of zy plus d of yx. From 1 and 2 will get, from 1 and 2 we get d of zx is less than r, and therefore z belongs to SRX. There is no any restriction on z, for any z belongs to SR1Y. This implies SR1Y is subset of SRX. Okay, SR1Y is subset of SRX. So that's what we proved. Thus, for any y belongs to SRX, there exists R1 greater than 0 such that SR1Y is subset of SRX, and therefore SRX is open set. Okay, SRX is open sphere. Thus, every open sphere is open set. Every open sphere is open set. Now we'll take the next theorem. Any non-empty set G is open. Any non-empty set G is open in metric space XD if and only if it is expressed as union of open spheres in X. Union of open spheres in X. Open spheres in X. Okay. So we'll take firstly necessary condition. We'll assume that suppose G is open set in X. Okay. So necessary condition. Suppose G is open set in X. Suppose G is open non-empty set. Non-empty in metric space XD. Then for every x belongs to G, there exists Rx greater than 0 such that open sphere about X with radius Rx is containing G. This implies union of SRX X belongs to G must be equal to G. Thus, G is expressed as union of open spheres. Union of open spheres in X. So any non-empty open set is expressed as open sphere in X. Okay. Conversely, sufficient path. Conversely, suppose G is union of open spheres. G is union of open spheres in X. Claim G is open set in X. Now since union is every open sphere is open set in metric space, and moreover union of open sets is open set. Therefore, by hypothesis and these results, G must be open subset of X. G must be open set in X. Is it clear? So, we have proved how G is open set in X. How G is open set in X. Our next result is that if I take any non-empty open set in Ru, then we have to show that it is expressed as countable union of open intervals in R. Okay. So next theorem, any non-empty subset, of Ru is expressed as countable union of finite or countable union of open intervals in R. Any non-empty open subset, open. So let G be non-empty open subset of Ru. Okay. Let G be non-empty open subset of Ru. What we express it as finite or countable union of open intervals in R. It may happen that G itself is open interval, then we are through. Okay. So case 1, if G is open interval, then the result hold. Case 2, if G is not open interval, then for X belongs to G, there exists R greater than 0 such that open sphere about X with radius R, which is equal to X minus R2 X plus R, is contained in G. choose the biggest interval, open interval in G. Say Ix containing X. Okay. Choose biggest open interval in G containing X. Say Ix. Say Ix. Then for any Z belongs to Ix, Ix is equal to Iz. Ix is equal to Iz. And for Z belongs to G minus Ix, Ix is not equal to Iz. Ix not equal to Iz. Okay. So from this, the collection C is equal to Ix when X belongs to G of distinct intervals is such that union of Ix must be equal to G. Must be equal to G. It is possible. Okay. Now choose a rational number XR belongs to Ix. Then Ix is equal to IXR. Ix is equal to IXR. Okay. Now since set of rational numbers is countable set, okay. No, sorry. Then C is equal to IXR, where XR belongs to G rational, is such that union of XR belongs to G must be equal to G Ix intersection Iz is phi here. That must be phi. Okay. Now since set of rational numbers is countable, therefore C is collection of countable number of subsets, finite or countable number of open intervals such that G is equal to union of IXR. XR belongs to G. Hence the proof. Hence result is proved. So with this discussion, the basic theorems related with open sets we have completed. By using open set, we are going to define concept of closed sets. Complement of open set is called as closed set. So our next concepts will be interior point, limits point, closure of set, then closed sets, etc. So till that, try to solve this exercise. So what is the exercise? For xy belongs to set of real numbers, let d of xx is equal to 0 and d of xy is equal to mod x plus mod y, x not equal to y. Then show that 1 D is metric for R second. SR 0 is equal to minus R to R. Third, SRA is equal to just singleton A set where R is less than mod A, 0 less than R less than mod A, and A not equal to 0. A not equal to 0. Open sphere is just singleton set here. So with respect to this metric, every singleton set other than 0, okay, that is every singleton set except 0 is open in RD. 4. SRA is equal to, say, minus of R minus mod A to R minus mod A union A for any R greater than mod A. For any R greater than mod A. So try to solve this example. It is a different example. So for getting some counter examples, this example will be useful. It is just like as a discrete metric space. So with this discussion, we'll stop here. Stay at home, stay healthy, and enjoy our online teaching. Okay? Go through all lessons, all sessions to understand concepts of metric spaces. This is my request to all of you. Thank you. Bye-bye.